So here we go. In unit vector notation, we have the two vectors, a and b. Vector a is 4i minus 3j. Vector b is 6i plus 8j. So we're given the two vectors in unit vector Cartesian notation. And here's the actual question. Determine the magnitude and directions of the following. We have A, B, C, D. It'll have a bunch of little parts. Magnitude and direction of vector A, that's part A. Vector B, that's part B. Part C, we have A plus B. We're going to add the two vectors and find their magnitude and direction. And then part D, we're going to subtract B minus A, find that magnitude and direction. And finally, in the last part, part E, we'll take A minus B and find that direction. So we'll subtract the vectors both ways, find their magnitude and direction. Finally, compare the orientation of part D and part E when we do the subtractions. Now, believe me, I know this is confusing. So what we're going to do is we're going to first start by writing everything down. We have vector A. I'm just writing down from the problem. We have 4i minus 3j. So here's a coordinate unit vector notation. And then we have vector B, which is 6i plus 8j, like this. So here's two vectors. Now what we want to do is part A and B and C and so on. So let's write those down. So we want to find the magnitude and the direction of, in part A, let me go ahead and just erase this, make it a little bit cleaner. Let's move a little bit down. We're going to find the magnitude and direction of vector A. For part B, it'll be vector B. For part C, it will be the vector A plus B. For part D, it'll be the vector B minus A. And for part E, it will be A minus B. So you see we have vectors for every one of these parts. Vector A, vector B, then we're going to add the vectors, then we're going to subtract the vectors both ways, B minus A and A minus B. And for all of these, we're going to find the magnitude and the direction of the resulting vector. And then it says we want to compare the directions. We want to compare the directions in part D and E when we do the subtraction both or two different ways. So let's start with the easiest thing first. We're going to start with part A, of course, right? And we could just see right here what vector A is. It's 4i minus 3j. How do we find the magnitude and direction of this vector? So first of all, this vector, 4i minus 3j, this completely tells us in space where the vector is, the x component and the y component here. But we want to change this representation to a magnitude and a direction. For the magnitude, what we're going to do is we'll say the magnitude, you can put a little magnitude bars around A if you want to. You can put the square root of the components squared. So it's 4 squared. The y component is actually negative 3, so the negative 3 is squared. This comes from the Pythagorean theorem. Add the squares of the components, take the square root. So what do you get? You get magnitude of A is, inside of here we have 16 plus 9, right, which is the square root of 25. And so the magnitude of vector A is equal to 5. All right, magnitude of A is equal to 5. So that's part of the answer because we want to find the magnitude and the direction. How do we find the direction? So the direction, angle theta, is going to be equal to the inverse tangent of y divided by x, because remember, it forms a triangle, the y component and the x component. When you draw the vector, forms a right triangle. The y component's negative 3, so it's going to be negative 3 on the top, and on the bottom, it's going to be 4. Notice how I'm kind of accelerating the problem a little bit. In the first few times we did this, I wrote down the component squared, and then we plugged it in here. And then I also did the inverse tangent of the y component divided by the x component, and then I plugged it in. Here I'm starting to do more what you would actually see on your paper. You should know by now that to find the magnitude, you have to take the square root of the components squared. You just stick it in there into the first step. The inverse tangent of y divided by x, just stick it in there on the first step. So I'm kind of like doing it more like we would do it in your actual paper there. So the inverse tangent of negative 0.75. All right. So whenever you take the inverse tangent of negative 0.75, what you get is negative 36.9 degrees. Right? And so what you have to ask yourself every time you take the inverse tangent of an angle is you have to make sure that the calculator is giving you the correct angle for where your vector actually is pointing. So you have to think about it, right? And sometimes, most times actually, it's good to draw an actual little diagram here. So if we draw, you can just do a tiny little sketch. Notice how small it is. Nothing fancy, right? It's 4i minus 3j. That means positive in the x direction, negative for the y direction. So it's like positive 4, negative 3 here. And so that means the vector is going to point somewhere down here. So that's a negative angle with respect to the x-axis. So this is telling me that I know that my vector is pointed in quadrant 1, 2, 3, 4, and this angle here is measures from the positive x-axis down, because positive angles this way, negative this way. This is the correct quadrant for where my vector is actually pointing. So I'm going to circle this, and I don't have to make any changes. But sometimes your vector is going to be pointed in a different quadrant than what the calculator gives you, and so that's why we have to do it every time. We have to check and make sure it's pointed in the right way. So vector A has a magnitude of 5 and an angle with respect to the positive x-axis of negative 36.9 degrees. All right, moving right along. That was part A. Let's check out part B. Now we have to find the magnitude and direction of vector B, which is what we have here. So the magnitude of vector B is going to be equal to the square root of the components squared. 6 squared plus 8 squared. All right, and so what do we have here? 6 times 6 is 36 here. And so what you're going to have here is the square root of 36 plus 64, which is the square root of 100, right? And when you take the square root of 100, you're going to get a magnitude of vector B of 10. So this is one of the parts of the answer, right? The magnitude of vector B, the length of it, is equal to 10. Now, how do we find the angle? This is all going to become second nature. That's why we do it so much. It's the inverse tangent of the y component divided by the x component, so it's going to be 8 over 6. And so it's going to be inverse tangent. When you have 8 divided by 6, and you take the 8 divided by 6 is 1.333 repeating there. And so what you get here is you take this guy, take the inverse tangent, you're going to get 53.1 degrees. Of course, I'm rounding, okay? Now, we got our calculator to give us an angle back. So again, we always have to check, always, because half the time it's going to be wrong. So we have to look at our actual vector. Our actual vector is 6 plus 8. Both of these are positive. X component's positive, and so is y. So it's going to be pointing somewhere up here, right? 6 over and then 8 up. It's going to be in quadrant 1 is the only thing I'm trying to really convince myself of. And the angle that it gives me back is also in quadrant 1. So I'm comfortable saying that this is the correct angle for my vector, 53.1 degrees, positive with respect to the x-axis, and the magnitude is 10 there. All right? So far, we just handled the individual vectors. Now we have to add them together. So for part C, what we'll do is we'll add them together. So if we have A vector plus B vector, what do we have? Well, the A vector is 4i minus 3j. So I'm going to put that in parentheses, 4i minus 3j. And I'm going to add to that another vector, which is the B vector, 6i plus 8j. 6i plus 8j. I put the parentheses here just to kind of group it, but really they don't matter. I can just disregard them when I do the addition. And so A plus B, the vector resultant A plus B vector, is basically what I'm going to do is I'm going to add these vectors together. So I have a 4i plus a 6i. 4 plus 6 is 10, so it's going to be 10 in the I direction. Negative 3, positive 8. So negative 3, positive 8 is positive 5, and that's in the J direction. So it's 10i plus 5j. So this is the resultant vector, but the question didn't say just add it. It said find the magnitude and direction of that vector. So what I'm going to do here is I'm going to label this vector C. You don't have to, but I'm just going to label it vector C so I'm not writing A plus B down, constantly all the time. Although, I guess I could, you know what, it doesn't matter. Let me just do it. Do it like this. We'll do it like this. Okay? Just because I don't want to confuse myself with other letters on the board. So, what is the magnitude of this vector? Right? When I add these vectors together, they form a new vector. What is its magnitude? Well, it's the square root of the component squared. 10 squared plus 5 squared. And so what am I going to have? It's going to be the square root of, here's 100, here's 25. So 100 and 25. That's easy enough. I think we can all just do that in our head. 100 plus 25. All right, and when you take the square root of 125, what you get is 11.2. Of course, I'm rounding, but this is the length of the that new vector that is formed, the magnitude of it. So I'm going to circle this. So we're trying to convert it to magnitude and angle. How do I convert it or figure out what its angle is? Well, the angle, whatever it is going to be equal to the inverse tangent. By now you should know it's the y component over the x component. So it's 5 over 10. And you all know that this is just 0.5, so that's going to be the inverse tangent of 0.5. Take 0.5 inverse tangent, and what you get for theta is 26.6 degrees. Now again, the calculator gave us back an angle. We have to check the angle. So we take a look at where is this vector actually pointing. It has an x component of 10 and a y component of 5. So that's like 10 up here, and this is like 5 for the y component here. So it's pointed somewhere like this. It's in quadrant 1. This is a 26-degree angle. That's in quadrant 1. So this is correct, and I'm not going to make any changes to it. You see where I'm leading up to. Eventually, here in the next little bit, we're going to get the wrong angle back, and we'll have to fix it. So far, all of the angles we've been getting back are already in the correct quadrant for where the vector's actually pointed. So for a plus b vector, I have a magnitude of 11.2 and a angle of 26.6 degrees. All right, let's take a look next. Do I want to do this on the next page? Let me see here. I only have 2 of them. Then I have to compare them. I think I'm going to do it on the next board. Yeah, I think I'm going to do it on the next board. All right, next, I want to take for part, this is part D, right? Part D. I'm going to take vector B, and I want to subtract from it vector A. Now, what is the A and B vector? This is the A vector, because we were adding A plus B. This is the A vector, this is the B vector. Here, I'm taking B minus A. So what I'm going to do is I'm going to group it, and I'm going to say this is vector B, 6i plus 8j, 6i plus 8j. And I'm going to subtract it from it a new vector, which is A, this one, 4i minus 3j. 4i minus 3j. These are just the original vectors given in the problem statement, nothing new. All right. Now the issue here is you're subtracting them, but this minus sign is just like any algebraic expression. This negative 1 here is sitting outside of the vector. You have to distribute the negative 1 in there before you do anything. So what you really have is 6i plus 8j, and then you have a minus 4i, and then the minus times the minus gives you plus 3j. All right, now you proceed. So you have b minus a. So you have 6i and negative 4i gives you a positive 2i, and then 8j and 3j, that's 11, positive 11j. So you have 2i plus 11j. Now this is the answer, the subtraction of these two vectors. This does tell me where the vector is pointed, but the problem wanted us to give it in magnitude and angle, just a different representation. Of course, this is the vector, but I just want to convert it because that's what the problem is asking us to do. So what we'll do is we'll say the magnitude of this vector, b minus a, is going to be equal to the square root of the x component, 2 squared plus 11 squared. Right? 2 squared plus 11 squared. So what you're going to have on the inside of here is you're going to have a 4 plus 121, 4 from here, 121 from here, and that is going to give you the square root of 125. And so magnitude of vector b minus vector a, when you take a square root of 125, you're going to get 11.2. 11.2, that is the magnitude of that guy. Now, how do I figure out what the phase is? Well, the angle here for this guy is inverse tangent of y over x. The y component is 11, and so it's over 2. Okay? And then when you take, in the calculator, 11 divided by 2, you're going to get 5.5. And when you take the inverse tangent of 5.5 for the angle, you're going to get inverse tangent 5.5, just double check myself, 79.7 degrees. Now before we circle it, we always have to check when we get an angle back. So let me draw a little xy. The vector that we have is 2i, 7j. So it's something like 2i and 11j, sorry about that. 11 is like up here for the y component. So this vector is pointed up very steeply, but it's still in quadrant 1. This angle is almost 80 degrees. So this is 90 degrees, so this is a little bit less than that. So this sketch means that this angle here for this vector is exactly what the calculator gave us back. So again, we don't have to make any alterations. So for the vector b minus a, the magnitude is 11.2 units of whatever distance we're talking about, whatever units we're talking about, and an angle of 79.7 degrees. All right, now for the next part of the problem, here we've done up to here, b minus a. Now let's take the vector a minus b. Now before you do anything, just think for a second. Because I know when you get started with vectors, you lose a lot of your intuition because it's a new concept. But all we've done here is we've taken vector b minus a, we got an answer. Now, what do you think is going to happen if we take vector a, if we flip it around? Instead of b minus a, we do a minus b. Now, I don't want you to answer yet because I don't think anybody knows enough intuition at this level, at this stage, to know what the answer is. But I want you to just expect that whatever answer you get should be somewhat related to this answer. It's not going to be the same, but it's going to be similar. Just think about 5 minus 2 and then 2 minus 5. The answers are different, but they're related to each other. One's negative, one's positive. So in this situation, since we're just flipping the order of the subtraction, we would expect the answer to be not something wildly different. We would expect it to be at least related. So let's see what we get. All right. So for the last little calculation we're doing, it's going to be, this is e, and so what we're going to do is take vector a and then minus b. All right, that's what we're going to do. So how do we do this? Well, here was b minus a, and so now we're doing a minus b, so let's just go in reverse order. 4i minus 3j, 4i minus 3j, close that off, minus this vector, which is 6i minus 8j. 6i plus, sorry about that, I think I said minus 8j. So we just flip the order of the subtraction, but again, we have to distribute this thing in. We always have to do that. So what we're going to get is 4i minus 3j. This becomes a negative 6i, and this becomes a negative 8j. Now we can do it. We have a minus b. Right? So what do we have? The 4i and the negative 6i, negative 2i. And then we have negative 3j and negative 8j, which means negative 11j. I'll just stop for a second. The answer that we got in unit vector notation, negative 2i minus 11j, before we had positive 2i plus 11j. So they only differ by a negative sign. So that is what our intuition told us. It should be related. And big surprise, you know, the example I gave, 5 minus 3 is 2. 3 minus 5 is negative 2. They differ, essentially, they're negatives of each other. And you can sort of see that that's what's happening. You could factor out a negative 1 here and show yourself that this is like the negative version of that. But let's continue on and do what the problem says. Let's change this into the magnitude and so on. So we suspect that we're correct, but let's just check. Magnitude A minus B. What's it going to be equal to? It's going to be equal to negative 2 squared plus negative 11 squared. Like this. Just this is a negative 2, that's the component, that's a negative 11, that's the component. But these numbers are all the same as before. So what we're going to have here, this is still going to give you a positive 4, and this is still going to give you a positive 121. So this is still going to give you the square root of 125. And notice that that's exactly what we got before. The fact that the components were negative somehow made the magnitude exactly the same thing. We're going to see why in a second. But the magnitude, A minus B, is equal to, when we take the square root of 125, we still get a magnitude of this vector of 11.2. So I'm going to circle that. That's the magnitude. Now let's calculate what the angle of this thing is. So the angle is the inverse tangent of the y component divided by the x component. Negative 11 divided by negative 2. Negative 11, negative 2. But notice that negative divided by negative is positive. So really, it's the inverse tangent of exactly the same thing as we had before. Here we got a positive 5.5, but here we also get a positive 5.5. And we still have to take the inverse tangent of this. So when we put 5.5 in the calculator and take the inverse tangent, what we actually get is, I'm going to put it over here actually, is we get 79.7 degrees. Let me just double check, 79.7 degrees. So it looks like we get exactly the same angle as we did before. Now let's check it, which is what I've been teaching you every single time to do. So what we're going to do is draw over here a little coordinate system right here, x, y. Where is this vector actually pointing? It's negative 2, negative 11 for y. So here, over here is negative 2, and then way down here is like negative 11. So it's negative 2 comma negative 11. This vector is actually pointing right here. That's in quadrant 3. But the calculator gave us an angle of 79 degrees, which is actually way up here. Let me draw that one. The calculator gave us a vector right here. The calculator gave us 79.7 degrees. Now, how is it that the calculator gave us the wrong angle? It gave us 79 degrees, which is clearly in quadrant 1, but my actual vector is pointed down here. You see, because all of these trig functions are cyclic. So if I keep putting, depending on the numbers you put in, it might give you an angle that's in an opposite quadrant, and here's the reason why. Because when we take a positive number and divide it by a positive number, we get an inverse tangent of a positive number. The calculator is going to assume that that means it's in quadrant 1 because it has to assume something. And so it gives me a single answer back. And it gives me the angle corresponding to the quadrant 1 position here. But when I take the inverse tangent down here, it gives me still an inverse tangent of the same exact number. So it again assumes quadrant 1 because it doesn't know, it doesn't know why you got 5.5. It just knows that here's a positive number and it gives me the angle associated with that. But I know that it's really not a quadrant 1 situation. It's not 2, 11, it's actually -2, -11. So what I have to do whenever I know, the calculator gave me this, but I know that it's exactly 180 degrees away, is I actually have to add 180 degrees to the angle it gave me, because the actual angle where my thing is actually 180 degrees bigger than that, because basically it's assuming a quadrant 1 situation. It's assuming the x and y kind of components you put in were both positive, but actually they were both negative. So when you take the division of them, the inverse tangent, you were taking the inverse tangent of the same number. It has to assume something, so it just gives you the smallest angle possible. So what we have to do is we have to say 79.7 plus 180. Because when we add angles, it's going more and more this direction. And so when we do that, when we take 79.7 plus 180, we get 259.7 degrees. This is the correct angle. And so now you can see why every single time, you know, back here, when we divided this and we got this angle, I said, check the quadrant. When we divided this and got the angle back, I said, check the quadrant. Over here, when we divided it, got the angle, I said, check the quadrant. And all the time that we were doing it, you're probably thinking, why is this guy telling me to check the quadrant? They're always correct. But clearly, they're not always correct. And it especially bites you. Well, it can bite you at any time, but in this case, it bit us because when we have both negative coordinates and the vector's really in quadrant 3, the calculator is going to assume it's in quadrant 1. You can have the same situation when they're catty-corner this direction as well. So check your angles, and you might have to add or subtract 180 degrees from it. So what we want to do now for the last part is the last part said graph part D and E, which is the B minus A vector and the A minus B vector. Graph them. We'll do a little sketch of them to see how they differ. But you can already tell that they sort of differ. The numbers are the same for the components, but they differ by a negative sign. Let's see what that translates to when we actually graph it. So I think the way I want to do it is, instead of being so tricky about it, is I basically want to rewrite this. So what I want to say is B minus A worked out to 11.2 and 79.7. So B minus A, both vectors, okay, we had 11.2 at an angle of 79.7 degrees, right? And then we had A minus B, which was also a magnitude of 11.2, but the angle was different. The angle that we got when we calculated it correctly was 259.7 degrees. 259.7 degrees. All right, so let's go ahead and see what these two actually look like and try to get some kind of intuitive understanding what it means to have subtraction of two vectors from different directions, or different order of subtraction. All right, so for the first vector, we have for B minus A, it's some magnitude, same magnitude for both vectors. The angle is 79.7 degrees. So this is 90 degrees, this is 45, so about 80 degrees is where this is at, somewhere like there. I mean, you don't have to be exact here, right? This, what we're going to call is vector B minus vector A, okay? And what we'll do is we'll label this 79.7 degrees, something like that, okay? Now the other vector, I'm going to draw it in, I think, a different color. The other vector, A minus B, is the exact same length. So it's the same length of the arrow, however the angle is 259.7. And we already know from the previous board that that differs from 79.7 by exactly 180 degrees. So this is the actual figure that we're going to reproduce over there. So what we'll do is we'll go here and we'll we know it's exactly 180 degrees apart, and it's the same length. So I'm trying to draw the arrow the same length, 180 degrees apart. Now that's not exactly right. You can see that they're a little bit bent. Sorry about that. I will try to do a little bit better, something like this. That's not exactly right. You get the idea. It's directly across, okay? This is vector A minus vector B. And this right here, if we measure from here all the way around here, is, what did we say, 259.7 degrees. But we know that these are 180 degrees apart, okay? Now, what does this actually tell you? It tells you what I was trying to illustrate to you, verbally a second ago. And that is that if I take a number, 7 minus 3, just think about numbers, what do I get? 4. But if I take 3 minus 7, I just flip the order of the subtraction. I get the same exact number, but I alter it by putting a negative sign there. That's what it is. And so if I represent this on a number line, which we did like in 5th or 6th grade, whenever you learned about negative numbers, what you learned is that 7 minus 3 was 4 units away over here. 1, 2, 3, 4. And then we have negative 1, negative 2, negative 3, negative 4 over here. So the way you would do this is you would basically say 7 minus 3 is 4, and we can represent that as, like, if you want to think about it in terms of a vector, you can think about it as a arrow that points to positive 4. And the 3 minus 7 being negative 4 is like an arrow that points to the negative 4. What does this look like? These are like two vectors, right? One is pointing towards positive 4, one's pointing to negative to the other direction. So they're exactly 180 degrees apart, point in opposite directions, but the same distance. It's the same thing going on right here. They're the same exact distance, they're pointed oppositely of each other. So if you have two vectors and you change the order of the subtraction, then what ends up happening is one vector is sort of like the negative of the other vector. And what have we already learned about? When we do vector subtraction, A minus B, what we learn if we do it graphically is the first thing is you turn B into negative B. So anytime you negate a vector, you just flip around its orientation. And so that's what we have here. This is flipped here. What we learned is that when we do the subtraction the other way, it's like taking the same vector and just making the negative version of it, which is like flipping it around, which means it points in exactly 180 degrees away, but exactly the same length. And when you look at the components of the vectors, you see the same thing. The component of this vector is 2i plus 11j. The component of this vector is negative 2i minus 11j. The x component was negated. The y component was negated. Now, does this make sense? Right? One of the vectors was positive 2 for x and positive 11. That puts the tip here. The other one was negative 2 and negative 11. That puts the tip here. So when you negate a vector, you're flipping the direction of the vector. We learned that when we learned how to add vectors a long time ago. When you do A minus B, first negate the B vector, turn it around, right? Why does it turn it around? Because when we negate a vector, what we're doing is we're negating the x component and the y component. And so if you have a plus 2 and a plus 11 and it points here, if I negate it by changing the x and y signs, then essentially I change it into the opposite quadrant, which flips it around, makes it point 180 degrees away, but yet have exactly the same magnitude. And all of that means when you take two vectors and subtract them in a different order, essentially you're taking the answer vector and you're getting the negative for the other answer. Exactly the same way that we have when we subtract and add numbers. I'm drawing parallels to numbers so that you can see that these vector ideas are not that different than what you already know in terms of numbers and number lines. Do I need you to memorize this? Do I need you to memorize it? When you take two vectors and subtract them, it does this? No, but I do want you to know why it can make sense and how it can make sense. So that like 6 years from now, you might be dealing with a problem with vectors and one of them is pointed here and you subtract them and then the other one's subtraction in a different way and it's pointed a different way. You may not remember what I'm saying here, but what you will remember is that, oh, we subtract vectors in the different order. It's understandable. It's not like a black box of confusion. So that you can then go back and review your notes or whatever and understand it. You're not going to remember everything through life. If I could remember everything I knew, then I would just be so happy because I would know everything. But I often forget lots of things. But what I do remember is, oh yeah, that really hard topic, I remember that I understood that. So I know that if I go back and revisit, it's understandable. So I'm trying to give you that confidence to know that these things are all understandable. So what I'd like you to do is solve this one yourself. I think it's a good problem. And then follow me on to the next lesson. We will wrap up and conclude the topic of adding vectors by components. learn anything at mathandscience.com.